8-3 common logarithms. Base 10 logarithms are called common logarithms and can be used in many applications. Common logarithms are usually written without the subscript 10. So in our previous lessons, you notice that I have been putting in there. You don't need to put it in there. Like on your calculator, you don't see log base 10 on there. You just see log, which is the common log. Most scientific calculators have that log key. So if I go to my calculator, you can see the log key. There's no base 10. But if you look above here, you can see 10 to the x power, which just means you do have base 10. The common logarithm of numbers that differ by integral powers of 10 are closely related. Remember that a logarithm represents an exponent. So for example, in the equation y equals log base 10 of x, y is the power to which 10 is raised to obtain the value of x. So the table here shows the relationship between common logarithms in exponential form. So log base 1 equals 0 because 10 to the 0 power is 1. Log base 10 of 1, log base 10 of 10 is equal to 1 because 10 to the first power is 10 and so forth. We're going to use that to help us solve these. It says use a calculator to evaluate log base 10 of 8 to the nearest 10,000. So how we're going to do this is you're going to press the log button on our calculator. So I'm going to hit the log and then insert the number. They want us to put log base 10 of 8 and then you hit enter. And it says to the nearest 10,000th place, so that's 4 decimal places. So this would equal roughly 0.9031. So tenths, hundredths, thousandths, 10,000ths. Letter B, we need to do log base 100, log of 100, 1, so 101. Nearest 10,000th, this would give us roughly 2.0043. Now this next one, use a calculator to evaluate log 23 to the nearest 10,000. So this would be roughly log of 23 gives us 1.3617. Next part, working with a word problem. Does the amount of energy E in Earth that is released by an earthquake is related to its Richter scale magnitude M by the equation log E equaling 11.8 plus 1.5 M. Although the scale was created in the 1930s, earthquakes that occurred before its invention have been estimated using the Richter scale. For example, the earthquake in Cyprus in 1222 is estimated to have measured 7 on the Richter scale. How much energy was released then? So if 7 is the measure or the magnitude, we are going to solve this. So log of E equaling 11.8 plus 1.5 times 7. So simplifying this, we would have 11.8 plus 1.5 times 7. This gives us 22.3. Now we need to get E by itself. So remember this has base 10. So if we exponentiate that with base 10, that undoes the logarithm. Raise this to the 10th power on this side, and we would have E equaling, and if we did 10 raised to the 22.3 power, we get a really large number. So we can put that in scientific notation. So we have like 1.995 times 10 to the 22nd power. If we were to estimate that, that would be roughly, so E would be roughly 2 times 10 to the 22nd power. Either one would be accurate. Next, the loudness in decibels of a sound is L equaling 10 times log of I divided by M, where I is the intensity of the sound and M is the minimum intensity of sound detectable by the human ear. If M equals 1 and a theater has movies playing at 95 decibels, what is the intensity of the sound as related to the minimum intensity that we can hear? Write your answer in scientific notation, the nearest tenth. So the loudness is 95. So I'm going to put 95 in for L equals 10 times the log. We need to find the I, and the M, they said the M was 1. So to simplify this, I'm going to have 95 equals 10 times, and here I can, actually, first thing I'm going to do is get the log by itself. So I'm going to divide by 10. So now I have 9.5 equals, and I'm going to use the property here, so that'll be log of I minus log base 10 of 1. And log of 1 is 0. So, and then you have log of I. So I don't need to put this here. Now all I have is 9.5. To undo a log, I have base 10. So that does that, and I'm left with the intensity equaling 10 to the 9th power, 10 to the 9.5 power would give us an answer of 316.2277660. If I were to put this in scientific notation, I move it 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be 3.2 times 10 to the 9th power. And this is what our intensity would be. Another one from example 2, a search engine ranks pages by their popularity by using a scale, where a site is given a rank R based on its visits per day V. The rank is related to the number of visits by the equation R equals log V plus 2. If a site has a rank of 5.5, then approximately how many visits per day does it get? So the R is the rank. So if the rank is 5.5, I'm going to have 5.5 equaling log of V plus 2. Get the log of V by itself by subtracting 2. I now have 3.5 equals log of V. Now I need to exponentiate this to get the V by itself. Whatever I do on one side, I do on the other. Now I have 10 raised to the 3.5 power, and that gives me, so approximately we get 3,162.27766. If I were to round that to the nearest visits, this would be about 3,162 visits. Moving on to our next example, it says solve these exponential equations by using logarithms. We're going to round to the nearest 10,000, so four places. So here, if I were to write this as a logarithm, I would do log base 11 of 101 is going to equal x. So on our calculator, we're going to type in logarithm. So log base 11 of here, so before we actually put it in our calculator, let me rewrite this. So we're going to do the log of both sides, and we're going to use log base 10. So this would be log 11, the x equals log of 101. Now from this point, since we have a exponent, we're going to use power or the property. So this would be x times the log of 11 equals the log of 101. Now to get x by itself, I'm just going to divide by the log of 11. And we'll get to this later on, but this is actually how you find the change of base formula. This would be x equaling the log of 101 divided by the log of 11. So now we grab our calculator and we're going to type in log of 101. Make sure you end the parentheses here, then divide by log of 11. And we get to the nearest 10,000, x would be roughly 1.9247. Next one, we would have log of 2 to the x power equaling log of 15. Put the x in front, so we have x times log of 2 equaling the log of 15. The x by itself, divide by log of 2. X would be roughly, so we do second, enter, change this to 15, and then this is log of 2. And we get 3.9069. Next, you can check this answer graphically by using the graphing calculator. Enter each side of the equation in the y equals list and press graph. Then use the intersect feature. So if we do that, so let's go back to the original problem here so we can see what our equations were. So if I go to here, y equals, if I put this as 2 to the x power, and the other one is 15, and then graph this, I have to change the, windows. The y maximum, let's make that 20 so I can see the 15 here. So we want to find out where it crosses here. So a second, trace, intersect number 5, hit enter. And we can see 3.9069. So this is where they would intersect. So that's another way of solving that using your graphing calculator. Next, solve this one. So for here, we do the same thing. So we would have, actually for this one, let's put it in our calculator so we can practice using our calculator on this one. So it's y equals, this would be 11 raised to the 2x power. I'll use parentheses, so 2x. And the other one is 9. Whoop, forgot to take out the 5. Now let's graph that. So here's the first one, here's the second one. Find the intersection, so second, trace number 5, hit enter 3 times. And that gives us 0.4582. Now, if I want to do it algebraically, this would be 2x log of 11 equals log of 9. Divide this by log of 11. So now on my calculator, if I did log of 9 divided by log of 11, and then I have to divide that by 2, you would get your same answer, equaling log of 9 over log of 11. Divide this by 2, which means I'm multiplying by 1/2. We get 0.4582. Either way, you can still get that same answer. Next, this gives us into our change of base formula, which allows us to write equivalent logarithm expressions that have different bases. Now, this is important, especially on a calculator, if you cannot change the base on your calculator. TI-84s, some of them you can put the base in there. 83s you cannot. So the formula for change of base is log base b of n. So when they say log base b, it just means that's really log of 10. So these have to have the same base. We're going to use log button, and then whatever is listed here of, that's your numerator, your a, whatever is in the original logarithm base, that goes on the bottom. So log of n divided by log of a. So here, if I want to use base a and I can't change it, I'm going to use base 10. So log of 17 divided by log of 8 will give me my answer. So to prove this formula, let log of a of n equal x. Here you can see the definition of a logarithm. You write log base b on both sides, then you use the power properties. So you put the x out in front here. So it's x times log base b of a equals log base b of n. To get x by itself, you divide by log base b of a on both sides, and there's our formula. So let's practice this. Log base 2 of 11 by writing in terms of common logarithms, which means log base 10, round to the nearest 10,000. So this would be log of 11 divided by a log of 2. So our calculator would give us log of 11 divided by a log of 2, nearest 10,000th would give us 3.4594. Letter B would be log of 52 divided by log of 6, which would be roughly the log of 52 divided by the log of 6. Again, make sure you end the parentheses for both of them. We get 2.2052. Next, evaluate this logarithm using the change of base formula. So this would be log of 30 divided by the log of 8. Grab our calculators. We have log of 30 in parentheses divided by the log of 8. And we get 1.6356. Example 5, still using the change of base formula, but using it in a word problem. It says the musical sense is a unit of relative pitch. 1 octave consists of 1200 cents. A formula to determine the difference n in cents between two notes with beginning frequency A and ending frequency B is n equals 1200 times log base 2 of A divided by B. Find the frequency pitch A if pitch B is 1661.22 and the difference between the pitches is 1600 cents. So you use the formula there. N is the difference, so I'm going to put 1600 in for n equals 1200. And then this is log base 2 of, I need to find A. B is 1661.22. So first thing I'm going to do is divide this by 1200. So with 1600 divided by 1200 gives us 4/3. So I'm going to put 4/3 here equals, now I have log base 2 of, and I'm going to separate those. So this would be log base 2 of A minus log base 2 of 1661.22. Now from here, I'm going to use the change of base formula. So this part right here will be log of 1661.22 divided by 2. This will be log of 2 here. Since this is a minus sign, to get all this to the other side, I'm going to add all of this to over here. So I'm not going to do any estimation until a little bit later here. So I'm going to do, it's going to be 4/3 plus log base, or log of 1661.22 divided by a log of 2. And then all of that, that's going to equal to log base 2 of a. I have to exponentiate that to get a by itself. That means I have to exponentiate this. So I'm going to raise 2 to that power. So I'm going to grab my calculator and I'm going to put in 2 raise, and then in here I'm going to have parentheses 4 divided by 3 minus, and then parentheses, I'm going to have log of 1661.22 end parentheses divided by log of 2 end parentheses end parentheses. And when I hit enter, let's see, that didn't give us the correct answer that I was looking for on that one. Let me just do it a different way here. So let's do 4/3, not minus, oh, I see where the problem was. Let me clear this. So hit second enter. I used the wrong sign up here. It's not 4/3 minus, it's 4/3 plus. Now if I hit enter, there's the answer we're looking for. A is going to be roughly 4,186. And I'll just keep it at 86 there. We did put decimals. We could put decimal. That'd be 0.01. This would be hertz or HZ. That's one way of doing it. The other way would be to graph it on your graphing calculator and find out where they meet. So here again is another way. The steps of solving that. These are the same steps we were using here. And then if you use your calculator, you can put each side as a function. So if I went back, this would be one equation, and this would be your other equation. And when you graph and find out the intersection point, here is your solution. Here's your 4/3. Here's where our answer was. Another one, function f of x equaling -3 plus 16 times log base 12 of x gives the estimated number of Canadian geese in a state park, where x is the number of years since 2010 and f of x is the population in hundreds. Write a function that represents the situation and is written in terms of common logarithms. In what year will the estimated Canadian goose population at the state park exceed 1,500 geese? So I'm going to put 1,500 in for f of x. And then I have -3 plus 16 log of 12, log base 12 of x. First thing I'm going to do is going to add 3 to both sides. And now I have 1,503 equaling 16 log of 12, base 12 of x. To get the log by itself, I'm going to divide by 16. Now I have 1,503 divided by 16. Here, so we have 1,503 over 16 equals log base 2, or log base 12 of x. Here I'm going to make a quick adjustment here. So when I put 1,500, Remember, the population is in hundreds. So this is already in hundreds. So that means this is actually 15. So that means if I add 3, that gives me 18. Then divide by 16. That's going to give us 9/8. Here's a reduced fraction. Remember, this also has to be, says exceed that, so it has to be greater than or equal to. So I'm just going to change that to greater than or equal to. So now I have here, and I need to just adjust this. So this would be change of base, which would be log of x divided by the log of 12 has to be greater than or equal to 9/8. Now I can use that to simplify. Here, if I were to multiply by a log of 12 on both sides, so now I have 9/8 times log of 12. That would give us roughly 1.2141. And over here I have log of x. Raise each of these to the 10th power. Exponentiate here, the log base 10 brings the x down. X has to be greater than or equal to, and then 10 to the 1.214 power. So 10 raised to the 1.214 power gives us 16.37, so roughly 16 years. So we have to do 16 years after 2010. 2010 plus 16 years would be roughly 2026. And our last question, the revenue of a company is R equaling 227 plus 44 log base 5 of x, where R is the annual revenue of the company in thousands and X is the amount spent on advertising in thousands. Use the graphing calculator to determine the amount spent on advertising if the revenue for the company is 325,000, round to the nearest dollar. So the revenue is 325,000, so I'm going to write 325 here, because remember R is in thousands. So it has to equal 227 plus 44 log base 5 of x. I'm going to subtract 227. So 325 minus 227 gives us 98 equals 44 log base 5 of x. If I divide by 44, 98 divided by 44 gives us, it's a fraction, we'll just do 49/22. So 49 over 22 equals log of 5 of x, which I can write this as log of x over log of 5. Now we're going to use our calculator here. So the y equals, let's clear what I have in here. So this first one, we're going to do 49 divided by 22. The other one, we're going to do log of x divided by the log of 5. We hit graph. Might have to change my settings a little bit here. Yep, so let's change our Windows settings. Let's do the maximum. Let's make that 20. The Y maximum, let's make this 10. Now let's graph that. Still need to go further. The Windows setting the X maximum. Let's make that 50. And let's count by fives. And let's change this to 100 will come by tens. Okay, now second trace, intersect, and enter 3 times. And we get 36.041. So remember that's in thousands. So if I multiply that by 3, or multiply it by 1,000, we would have x equaling 36,041 dollars. That's our lesson on common logarithms.